Hey friends, it's good to be back with you. And today I'd like to take a deeper dive into integration and more specifically into numerical integration. Now, as we mentioned before, some functions you can do symbolically. Now, when I say symbolically, I mean pushing symbols around on a piece of paper or using the symbolic processor in MATLAB. But it can be hard, and for many equations, you just can't do it symbolically. There is no symbolic answer. So in practice, most of the time, you're going to be integrating numerically. Well, if you're going to spend most of your time doing that, it seems like it's worth digging into the details a little more. That's what we're about to do. So earlier, we talked about Riemann sums, which is just adding up boxes, and touched on trapezoidal rule. Well, there are some other possibilities here, and they are midpoint rule, trapezoidal rule, Simpson's rule, and then we're going to talk about convergence a little bit. So let's start with midpoint rule, which is just a different take on Riemann sums. Here's what it looks like. So if I have a function here, I'll draw this on my little board. That's x and that's y, and I have, there we go, and I have some function here, whatever that is. When this function means something that we care about. It could be something physical, it could be accelerations of a plane, it could be fuel consumption on a car, it could be a lot of things. And so the way Riemann sums work, which is the basis of integration, so we just divide this up into even segments there, and these are all delta x wide. And then just draw a box, put a horizontal line on top of each one of those to make it a box. Well, how do we do that? Well, before we used the left side of the segment here and just drew a box like that. Here's what it looks like. So this one would be there, and there, and there, and there. That's what it looks like. Well, how good an approximation is that? In this case, probably not very good. And the reason is that there's all these errors here. Okay? Those spaces, those areas that I'm highlighting here, aren't accounted for. That's where the box is wrong. It's an approximation, and here it's not a very good approximation. Well, what's another way to do this? Well, there's nothing magical about saying that the left-hand side of each interval, each little segment, has to be the height of the box. We can pick any value we want. Well, the midpoint rule says, what about putting it in the middle? Let me erase and draw this again, okay? Okay, hopefully that's close enough. Once midpoint rule is just about what you think it is. Rather than taking the left side of the box, let's just take the middle. There's nothing wrong with doing it that way. And we're going to set the height of the box based on the middle of the interval rather than one end. And the hope is that by doing that, the positive and negative errors cancel out. Well, what do you think? Here's a place over here where the box overestimates the height, and right there it underestimates. Well, do those cancel out? Yeah, maybe, but they come closer to canceling out than using the left side. So that'll work. Well, that seems like it ought to work pretty well. We're going to try it here in MATLAB in a few minutes. Well, another way to do this is trapezoidal rule. Now, in case you didn't see the previous video, let me erase and I'll do this again showing the trapezoidal rule. So just give me a second here. All right, so here's our function again, pretty much. It's close enough, I guess. And rather than using a horizontal line for the top of the box, we're going to use a sloped line. And rather than just using one point, we're going to use both ends of the box and just draw a straight line between them, like this. Now, where the curvature is negative, you're going to underestimate the error. Where the curvature is positive, you're going to overestimate the error. By the way, do you know how to tell the difference between positive and negative curvature? Curvature is just the second derivative of the function here. Here's the stupidest thing I'm ever going to write on the board in this class, but you're going to remember it. Here's how you remember positive and negative curvature. So positive looks like this. Negative looks like that. You may see where I'm going here. Positive curvature makes a smile. Negative curvature makes a frown. Dumbest thing you're going to see in this class, but I bet you'll remember it. So anyway, here, by using a sloped line, we're getting closer and closer to approximating the curve, and the errors are smaller. This is built into MATLAB. There's a command called trapz, which I showed before. We're going to go touch on it again. And there's another one, another approach to this called Simpson's rule. I mentioned it before in passing, but let's go into a little more detail. Just give me a second here. Okay, so we've got a curve, we've got some boxes drawn out or on the curve to approximate it. Let's look at this section of the curve right here. Okay, I'm going to call this x0, x1, and x2. Okay, that means this point here is y0, this point is y1, and that point there is y2. Right, so we've got 3 points in space that we know. Here, here, and here. We absolutely know what those are. We've calculated them. We've paid to calculate them. Well, if I have 3 points, that's enough to define a parabola, isn't it? Because remember, parabola is ax squared plus bx plus c. If I knew what a, b, and c were, I would be able to fit a parabola through that. Well, integrating parabola is dirt simple. You can do it symbolically, so you only have to do it once. Well, what if I were to draw a parabola through there, and then draw a second one through here, and just keep going? What that does is that has a curve approximating a curve. Now, is it the right curve? No, probably not. But a curve approximating a curve seems like it ought to be better than a bunch of straight lines approximating a curve. Most of the time, it is. So what are the mechanics of this? How would we actually do this? If we know x0, x1, x2, y0, y1, y2, how do we find a, b, and c? That's what we're trying to figure out here. Because once I know what a, b, and c are, I know everything there is to know about that parabola. Well, how about if I go over here? I'm going to erase this because we got this already. We don't need that anymore. And all I'm going to do is I'm going to write out 3 parabolas with that, because I've got 3 data points. Let's think about this a second. I got 3 data points, and I got 3 things I need to find. Seems like that ought to work. So let's do this. Okay, there's 1. I know y0, I know x0. Okay, that's so the variables here are a, b, and c. Okay, I know y1 and x1, and I know y2 and x2. Well, that sure looks like 3 equations and 3 unknowns. And because of that square, it's tempting to think this is a nonlinear system. This is not. This is a linear system. Because remember, my variables are a, b, and c. They're not x. X is a number. We know x. So that's a number, that's a number. A, b, and c are the variables. What would this look like? Well, I don't know. Could we write this out as a matrix? I bet we could. Oh gosh, I hope you can see that. Okay, I think you can. I'm just about running out of board here. But that sure looks like a matrix equation to me. Remember, these are numbers. We know what these are. those are the variables. So at every step, you can solve this. Now, you've got to invert a 3 by 3 matrix. It's not very hard. So we're getting to the point of diminishing returns here. Is this worth it? Maybe. Okay, well, these are the three methods. Now, the last thing we need to see is, what does a convergence plot look like? How do you know if you've converged on a solution? Well, I could, if I wanted to, I could make a plot that showed my estimate of the integral as a function of maybe the number of boxes, n. What would that look like? Well, let's try this. So this is now n, number of boxes. This isn't x. This is now the number of boxes, and this is estimated area. Well, what might this look like? Let's say my boxes are very, very wide. dx is large. Maybe I'll overestimate the total area. Well, as I decrease it, the area gets smaller, and you see sometimes convergence plots looks like that. When the line between these successive values of n goes to horizontal, you're converged. Adding more points is not going to get you a better answer. Now, does it always look like this? No. Sometimes it converges the other direction, like that, and sometimes you can see it zigzagging. So the convergence plots basically take three different topologies to have three different behaviors. So, okay, there's how to do this in principle. Let's go to MATLAB and try it there.